It's working, okay. Because of the lateness of the time, we don't want to continue this unduly, and we have a lot to hear from our speaker. I'll make a very short introduction of the speaker. David Olive had his undergraduate education, as I mentioned before, in Edinburgh. Around 57, he moved to Cambridge and did all the rest of his studies there, and he stayed there for some time. And he was working on analytic S-matrix for a while. Even there is a book authored, among others, by Olive on this subject, something called the analytic S-matrix. And essentially, he said the big change happened in '68 when he heard about the Veneziano formula, and he moved to duality, which was a natural thing to do for S-matrix people at the time, but he continued to work over the years on this and shifted to the more proper string theory. Let me first finish his formal CV. Between 71 and 77, he was at CERN, 77 to 92 at Imperial College, and from 92 until now at Swansea in Wales. I cannot even start listing all his many contributions. People know a lot of his work in connection with strings, with Shirk, on duality, on monopoles. Late in his life, around the age of 40, he switched to more formal thing. I mentioned a little bit this influence. And he has been doing beautiful work ever since on this subject. And there could be no more appropriate subject to commemorate Joe Dotan's memory than discussion of magnetic monopoles, something, a general area that he liked so much. So please, without further ado. Oh, and I should say that for the last 20 years he has been the member, an FRS, the member, a fellow of the Royal Society. So let me see. We should put it here. Yeah, we should touch here. That's somewhere here, I believe. Okay. Oops, sorry. I'm holding my glasses at the same time. Without the glasses, I don't see. Can you put it on?
I hope that works. Can you hear that? Very good. Well, it's a great honor to be here on this occasion. I did meet Joseph Dothan, but I can't say I knew him very well. But I met him actually, at least on the occasion that I first came to Israel, which was in 1971. There was a remarkable duality conference organized on this campus at that time, and we were both there. The theoretical particle physicist, theoretical particle physics is a fascinating subject, and I think one of the reasons is that it allows scope for imagination. Of course, physics is restricted by reality. It's restricted by experiment. But actually, experiments are very difficult to do, particularly in particle physics. And, you know, they can take 20, 30 years to do, because you might have to build a new particle accelerator, plan it, build it, commission it, and so on. So there's an enormous time lapse between conceiving of an experiment and doing it. And that provides an opportunity for a theoretical physicist. He has a time in which he can exert his imagination and produce interesting ideas. There is, of course, a discipline. I mean, he can't produce any idea. There is a discipline. His ideas have to make sense, and they have to be logical. And there is a very sort of tight mathematical logic that they have to obey. So it's not easy. But many people are attracted to that sort of situation, and I think maybe Joseph was attracted to it, and I certainly am. Now, there are actually, historically, there are many important examples of this sort of development. In my lifetime career, which started about the same time as Joseph's, the big development has been the standard model of particle physics. And the underlying principle there is that the fundamental interactions are what are called gauge interactions, and I'll be talking about gauge interactions. In particular, what is called the non-abelian gauge theory. And this was a very actual intriguing idea when I started as a research student. The first crucial published paper was by Yang and Mills in 1954. I started research in 1960, and here was this intriguing idea that there were these generalizations, this sort of generalization of electromagnetic theory with several gauge particles rather than just the photon, which is the gauge particle of electromagnetic theory. I'll say something about electromagnetic theory. In fact, I'll mainly talk about it, but there was this idea for a generalization. And many people were intrigued by it, but it was one of these ideas that on the face of it was wrong. In fact, it had already been discovered some time before Yang and Mills by Wolfgang Pauli, another Nobel Prize winning physicist. And Pauli didn't publish his work because he thought, well, he recognized it predicted a number of massless gauge particles, like the photon is a massless gauge particle. It, if you like, predicted more than one photon, and nobody had seen more than one photon, so he thought he couldn't dare publish it. And when he heard Yang propose this idea, he immediately got up and criticized it on these grounds, but Yang persisted. Yang and Mills, and also actually there was another guy called Ron Shaw who also discovered it in Cambridge and didn't publish it on the advice of his supervisor Abdus Salam. So there was this intriguing idea, non-abelian gauge theory. Everyone was intrigued by it, but it didn't fit the facts. And then eventually new people came along with new ideas. Peter Higgs, for example, developed what is called the Higgs mechanism, which solves this problem of the mass. It provides a very natural, appealing mechanism for giving these gauge particles mass. Still not sort of verified experimentally. It is because it predicts a new particle called the Higgs particle, which people are looking for in the new experiments, and well, they haven't yet seen, and they're hoping that they'll see it when more powerful experiments are switched on, as they will be shortly. And another development was something called asymptotic freedom, which I won't have time to talk about, but this was another unexpected property of non-abelian gauge theories, which enabled them to explain, when applied to QCD, quantum chromodynamics, you could explain the scaling properties of deep and elastic scattering. So, the people who proposed this asymptotic freedom, although their theory was back in 1971, they were only awarded the Nobel Prize 2 years ago. And actually, I attended the ceremony, so I saw them accept it. I want to talk about something else, a similar sort of idea, which is very attractive, very appealing, and it's been very attractive and very appealing for a much longer time, because the basic development was actually in 1931, before I was born. And this has to do with the magnetic monopole. It's not been disproven. It's very intriguing and very attractive, and it remains so after all this time. In fact, it gets more intriguing and attractive as new developments come along. In particular, we can see it in a new light now that we have this standard model that I mentioned with the non-abelian gauge theories. It fits beautifully into that too. So I want to explain something about this. Now, as I said, the non-abelian gauge particles are sort of like more complicated versions of the photon, and the photon is the particle of electromagnetic theory. If you quantize Maxwell's electromagnetic theory, you get a particle called the photon. Now, before the time I'm talking about, 1931, actually I think it was in 1925, there was an important development. Quantum mechanics was finally formulated in a sort of satisfactory way. I mean, the idea of quantum mechanics had grown up in the work of people like Einstein and Niels Bohr and so on, and many others, but it wasn't quite satisfactory, and eventually Heisenberg and Erwin Schrödinger found a satisfactory formulation. I won't explain what that is, but Schrödinger's formulation was completely different from Heisenberg, and at first people thought it was wrong or something completely different, but eventually it was understood it was equivalent. But it was based on something called the wave function, and that's always called psi. And so you're talking about an electron, and the important thing about the electron is that this is the particle which carries the fundamental electric charge. So it's the basis of electronics. I mean, electronic circuitry has to do with the flow of electrons around electric circuits. And the way to describe the electron is with a wave function. Now, in this formalism of Schrödinger, there was a peculiar feature which I don't know when people first realized that there was some peculiar feature which was apparent in this formalism, which actually wasn't apparent in the other formalisms like Heisenberg's. This wave function, it depends upon the coordinate in space-time, x. So you can think of that as space, or it can be space and time. But it's complex, and you can change the phase by multiplying it by a phase factor, and it doesn't actually alter any of the physics. So here is the ambiguity. You can multiply the wave function by this phase factor. That is just a sort of curiosity. At first it just seemed to be a curiosity. Of course, eventually it was understood, actually not by Schrödinger, but by someone else, Max Born, that to extract a physical quantity out of this wave function, you look at the modulus, or the modulus squared of it. You multiply this by its complex conjugate, and of course the phase factor cancels out. It doesn't appear in the probability. So indeed, this is an ambiguity. You can change the phase, and it doesn't affect the probability interpretation. So this was an important sort of insight in the early days of quantum mechanics. And here is Erwin Schrödinger. Now, when you stop to think about this change in phase, At first sight, as I wrote it down, the change in phase, which is this alpha, it's the same for all the points of space and time. Yet that sits awkwardly with something else which had been established before, some years earlier, which was Einstein's theory of special relativity. According to Einstein, light signals can't travel, no signal can travel faster than light, and light has a finite velocity, which is called the speed of light. It's given a symbol c. And because of that, there's something wrong about what I said in the previous transparency. If you change the phase of the wave function at one point of space, how would a neighboring point of space at the same time know? Because no signal could travel instantaneously from one point to another at the same time. So it sounds as if there's something fishy about that idea, that the wave function shouldn't depend upon the phase. And it took a while to figure out what the significance of that fishiness was. And it has to do with something, namely that since we're talking about the electron, it carries an electric charge, and therefore it couples to the electromagnetic field. And the electromagnetic field has electric components and magnetic components, E and B, as they're always called. And they're both three vectors, so there's a vector notation there to emphasize that fact. And these fields exert a force on the electron. You can tell the difference between the two fields by the nature of the force. It's different for the electric force and for the magnetic force. Now, these fields satisfy Maxwell's equations, which are equations discovered by James Clerk Maxwell in about 1860, about 60 years earlier than the time we're talking about, the time of the Schrödinger equation. And the magnetic field has a zero divergence, and that means that it should be possible to write it as, this is a mathematical notation, the curl of the vector potential A. So this A is actually going to be something rather important. It's called the vector potential. People already knew that this equation was important because, amongst other things, Maxwell had predicted that there would be wave solutions to his equations in which waves traveled at the speed of light, this finite velocity c, and they could do so with any frequency. So therefore, as well as describing the light with which you see me and you see this blackboard, there could be other frequencies which we couldn't see, and people realized maybe you could build devices that generated different sorts of electromagnetic wave, and of course they developed radio transmitters, and of course this equation was of fundamental importance in doing that. Now, there's another interesting person stepped into the story. There was a mathematician called Weil, Hermann Weil, who is a German, and he had he was a pure mathematician, but he had a sideline in theoretical physics. And when Einstein had produced his general theory of relativity, which explained gravity, he tried to develop that better. But actually, what he tried to find a sort of more geometrical explanation, but actually his ideas turned out to be wrong, as Einstein pointed out, and he had to accept they were wrong. But what he tried to explain was to incorporate the Maxwell theory into the relativity theory, to combine the two together as a geometrical picture. But then, something like 15 years later, he had a new idea, because he could take advantage of what Schrödinger had done with his wave equation and that ambiguity. And what Hermann Weyl pointed out was that I don't know how the arrow works. There's supposed to be a pointer, but I can point to it. Maybe this change of phase of the wave function, which is similar to what I wrote down before. Oh, I pressed. Oh, it's that thing. Okay. Maybe you could make the change of phase vary from point to point in space-time. So now the phase there varies from point to point in space-time. And what Hermann Weyl realized in a paper he wrote in 1929 was that you could correlate that with an alteration in this gauge potential, which I told you about on the previous page, which seemed to be very important in connection with radio waves. And in particular, you see that the phase comes in here because you have what is the gradient of the phase as the alteration of the gauge potential. And if you look to see what the magnetic field is, it's not changed because this term drops out when you take the curl. Now, here there is a slight complication because the gauge potential is something sort of semi-physical. You know how beta is normalized. We actually had to introduce some extra coefficients in there. Before we wrote I beta, but now it's IQ divided by H bar beta, and Q is the charge of the electron, and H bar is actually Planck's constant, which is something which comes up in quantum mechanics. Here is Hermann Weyl, two pictures of him. As you see, he's a much older person. Well, he's not much older than Schrödinger, but much older than Heisenberg and Dirac and the other founder figures of quantum mechanics, about the same age as Niels Bohr, or slightly older. He seemed to be a very interesting person. I don't know a lot about his life. I've read that he was a friend of Thomas Mann, the author. He actually was in the same, at the time that Schrödinger discovered his wave equation, he was in the same institute, which is ETH in Zurich, and reputedly the story is that they helped each other, but if I understand correctly, Schrödinger actually discovered his wave equation when he was went off on a skiing vacation with one of his students, leaving his wife to be cared for by Hermann Weyl. I don't know the full details of that story, but it is mentioned in some of the biographies. So anyway, he had inside information about quantum theory. Now, so I said that according to Weyl's idea, you can alter the phase of the wave function, but at the same time, to keep physics the same, you have to alter the gauge potential. And actually, there's more to the gauge potential I've said. I described a vector, 3-vector gauge potential. You can actually make it into a 4-vector and generalize the equation in that way to take into account relativity. And the connection between the gauge potential and the field strength, which out of which E and B are formed, is such that when you do this alteration, the terms involving beta cancel out, and so the field strength is unaltered. And, well, this is a bit formal, but if you put these equations together, there's a derivative of the wave function called the covariant derivative, a sort of combination like that you can form. And you can check if you do these two transformations that just changes by a phase, just like the wave function does. So this equation is the same as this equation, and you've taken into account the fact that you differentiate the wave function in doing that. So that was an important notion. And so I think Weil sort of enunciated the idea that maybe it was fundamental that physics should be invariant under these transformations, and it would restrict the sorts of equations you could write down. It was actually a new principle, and actually it's possibly seems to me the only new fundamental principle that has been developed into physics since quantum mechanics. And it is the principle, it's this idea which Pauli and Yang and Mills and so on extended to derive this concept of non-abelian gauge theory, which came into QCD. So that idea of Weil's was very important. I think the importance of the idea wasn't realized until after he died, so he was never, of course, awarded the Nobel Prize, and maybe wasn't considered for it, I don't know, but I think if people could sort of rewrite history or award prizes posthumously, they would look at him. Now, so you can read that first sentence. The second sentence is what I've just been saying, that I think it is an important new principle, but the fundamental idea actually was suggested to Weil by Einstein's theory of general relativity, which I've also mentioned to you, and I've told you something about Hermann Weil. This crucial paper he wrote in the United States. I think, no. He had been in Zurich, and he had also been in Göttingen, but he was visiting the United States, and sometime after the time he wrote this paper, maybe 5 years later, I'm not quite sure of the exact time, no, maybe it was even later, there was this institute in Princeton set up, the Institute for Advanced Study, which one of its first moves was to attract Einstein to a position there, and shortly afterwards Hermann Weil was appointed to a position there. So Hermann Weil and Albert Einstein were colleagues and presumably friends. So I will say something about this extension of this gauge principle to the non-abelian case, because I want to sort of emphasize there's a continuity of ideas in theoretical physics. This, of course, came, Weil's idea was in 1929. This was proposed in 1954. You can these phase factors, when you can multiply two phase factors together and you get a third phase factor. That means that the phase factors form a group, actually an abelian group. Now, what Hermann Weil was famous for was actually the theory of non-abelian groups. He developed a comprehensive representation theory of them. That was his sort of professional occupation. And, well, he didn't think of this, but it's difficult to understand why he didn't. Why not replace the idea of the phase change of phase by changing the Where's the... Okay. Oh, yes. Why not have a wave function which is now a column vector instead of just one component thing, and you change it by a matrix? And of course, if you do two successive transformations like this, you get the product of two matrices, and the product of two matrices is a third matrix, square matrix. And that's a basic thing you do in group theory. And this is the idea of Yang and Mills and Shaw and Pauli and so on. And then, I won't write it down, but it requires you to have non-abelian gauge fields, non-abelian now because you have these sort of matrices, and matrices don't commute with each other, and non-abelian just means they don't commute. The matrices, these matrices, you can multiply them together, and that's the way you form the gauge group. Product of two matrices is a third matrix. And if you think about that idea, as people eventually did, and of course you do a lot of work with the basic phenomenology of particle physics, look at the weak interactions, try and figure out the strong interactions, people eventually in the 1970s formulated what was called the Standard Model. It's a very non-abrasive subject title, which obviously appealed to the authors, and it's supposed to describe all the forces of nature except the gravity forces, which are in fact described by something similar, because in some sense general relativity of Einstein is some sort of gauge theory. And so it's like electromagnetic theory, in fact, the Maxwell theory. Maxwell wrote down the equations for the electromagnetic field, and Dirac wrote down the equation for the wave function, the electron wave function, taking into account relativity. I haven't written that equation down. And you can generalize those equations to this more complicated situation in which the gauge group is non-abelian instead of abelian. And this gives you part of the Standard Model, but there are some other things that come up. There's the Higgs mechanism, which accounts for the masses of the gauge particles and the patterns that seem to fix what we know. And the electron has to be replaced by a set of particles called quarks. And the quarks have to have a property called color, which has to do with the gauge group of the strong interactions. And there's yet another sort of hidden property, the one that got the Nobel Prize only 3 years ago, the asymptotic freedom. So conceptually, it's all actually related to general relativity. I like to say that because, you know, it's nice to emphasize that actually there's a logical coherence to all these ideas that have developed in particle physics. There have been sort of some blips in the historical development, but we've learnt this wonderfully sort of coherent theory, which is mathematically coherent and which passes many, many experimental tests. And if you try and work out how many people earned Nobel Prizes with this story, I think you have to say there's more than 20. Now I want to step back a bit in history and look at a question that Dirac asked. Dirac was impressed by this proposal of Hermann Weyl about the gauge principle, which I've told you about, which can be developed to give you the Standard Model. He said, what if the divergence of the magnetic field is zero? It's usually zero, and that means there's no magnetic charge around, because anything non-zero would be regarded as a source of magnetic field, and hence a magnetic charge. And I don't know if I can draw a picture. Is there? It's important to. So, supposing there's a point at which the magnetic field doesn't vanish. So there's one point where there's a magnetic charge. It's concentrated at a point, And supposing we surround it by a sphere, and that's a semicircle surrounding, but now I fill in the top hemisphere and the southern hemisphere. We usually call the top one the northern one, and this is the southern hemisphere. Sorry, yes, and the two hemispheres intersect on the equator. The equator is this circle which I first wrote. So have in mind that picture. Now, you have to be very careful. People thought that you can naively think that if div B vanishes, that you can write the curl B equals the curl of A. It certainly follows that if B equals the curl of A, div B vanishes. But you have to be very careful about reversing that argument. And actually, it only works in a simply connected region. That means a region which you just get by sort of enlarging a point. That's a very subtle point. It's all to do with this homology and stuff which we heard about in the introduction. So this idea of Dirac was actually proposed before these words, homology, homotopy, were even developed. So it was the sort of predecessor of this branch of mathematics. The magnetic charge has to be the flux of the magnetic field out of this sphere which I've drawn. That's sort of elementary thing. And if B could be written as the curl of A all over the sphere, automatically that would vanish because that would just integrate by parts to zero by Stokes's theorem. So the conclusion is that you cannot write B equals curl A all over the sphere. You could perhaps write it on the northern hemisphere and write it in a different way on the southern hemisphere, a different A. That would be okay. So this is what I've done here. I've written B equals curl the northern gauge potential in the northern hemisphere, and B is the southern one. And these can't be the same, because if the northern and south potentials agreed with each other on the equator, then this argument I've just given on the previous transparency would say the magnetic charge was zero. So, but they must give the same B on the equator. There's a unique B on the equator. How could it be that you had two different gauge potentials? Well, of course, it could be that they differ by a gauge transformation, the gauge transformation I told you about earlier. And there you are. It must be that on the equator, the northern gauge potential differs from the southern gauge potential by a gauge transformation, which means the gradient of this function beta. Let's work it out, what happens to the magnetic charge. And there it is. It's the sum of the northern hemisphere plus the southern hemisphere contribution. And we can use Stokes's theorem to work those out in terms of the appropriate gauge potentials, and we actually get the difference between the north and the south gauge potentials on the equator, integrated around the equator. But this difference between these two is what is given by the gauge transformation. So that just integrates to be the jump of the gauge transformation. So the magnetic charge is equal to the jump of the gauge transformation as you run around the equator. If the jump was zero, then you would get zero. That's the situation we had before. But maybe the jump needn't be zero. Now, we have this electron wave function, and of course it's to find in the north hemisphere and the south hemisphere, and it must be related by a gauge transformation, and this is the gauge transformation for the wave function. I told you that before. Now, as we go round the equator, of course this phase changes, but the point is when we go around the equator, we must eventually get agreement, and that requires that the jump, the variation of the phase as you go around the equator, which is this, is e to the iq divided by h bar times the jump in beta. That must give you a factor 1. But we proved on the previous transparency that the jump of the phase was the magnetic charge, G. So therefore, this factor is 1. This, you have the I, you have the charge of the electron, you have the magnetic charge, and you have Planck's constant. That combination has to be 1. Just by sort of very, well, slightly sophisticated mathematics, but once you understand what the symbols are talking about, it's something you can't argue about. And that means that this phase here, the only way for it to be 1 is that it's an integral multiple of 2 pi. So you get the conclusion that the electric charge times the magnetic charge is 2 pi times Planck's constant times some integer. And that is what Dirac discovered.
There should be a 3 there between 2 and 4.
Oh, there should be. Yes, thank you. There should be a 3 between 2 and 4. Well, take that as read. So this is what Dirac realized. It doesn't have to be 0. It could be 0, but it doesn't have to be. You could have these integers. And that was an amazing new thing. So here is a picture of Paul Dirac. I think this is obviously of him as a young man. It's probably about the time that he was awarded the Nobel Prize, which was about the time that he wrote this paper. I should mention that he taught me. When he taught me, I realized he was much younger than I am now, so that's a chastening observation. He was 10 years younger. Anyway, here, so this is his quantization condition. This time there's a 3 magically occurred. So if it is true that you can have a magnetic charge, and no one has actually seen one, but if it's possible, and this equation allows it, you see something interesting, because you can divide the equation by this non-zero value of the magnetic charge, and you find that the electric charge always has to be an integer multiple of 2 pi h bar over g. Whatever particle you're talking about, because you could apply this to all the different electrically charged particles in the universe if you had your standard magnetic charge. So you see, dividing 2 copies of this equation, you find that the ratio of 2 electric charges has to be a ratio of integers. In other words, the ratio of any 2 electric charges has to be a rational number if there is a magnetic monopole in nature. And that's true. I mean, it's a fact. It's one of the most basic experimental facts there is. It's true to enormous accuracy. The electric charge of the proton is minus the electric charge of the electron. The electric charge of a nucleus is equal to the total charge of the constituent protons, which means minus the atomic number times the charge of the electron. And this is sort of verified, because if it wasn't true, if there was a slight discrepancy, our planet would disintegrate and we would have disappeared, well, long, long ago. The Earth couldn't exist. So this is known to be true to extraordinary accuracy. And this is the only explanation of it, this argument about the magnetic charge. So it's fundamental to our existence, this equation, this, which follows from the existence of a magnetic charge. Of course, it doesn't imply the existence of the magnetic charge, but it makes it very difficult to imagine there's any alternative explanation. And nobody has found an alternative explanation. They've had 75 years since Dirac's paper to think of an alternative explanation of this quantization of electric charge. Of course, people have found explanations, but it's always turned out after some further insight that actually they're equivalent to Dirac's argument, so they're not any different. So there's no new explanation. I'll just make a comment about grand unification. This is the this is the standard model here. The gauge groups actually have specific names. U2, that's the electromagnetic gauge group, and SU3, that's the strong interaction gauge group. And in grand unification, it's imagined that they are subgroups of some larger group, which is what's called a simple gauge group. And with this picture, you can, without Dirac's argument, you can explain the quantization of electric charge. But actually, it was discovered in 1973 by 't Hooft and Polyakov that there are magnetic charges in this theory which arise as soliton solutions. So Dirac's argument is still actually valid. So this is what I meant by a new explanation turning out not to be new. Now, I want to talk about some more modern ideas, and this is something I have been interested in. Supposing you look at the simplest version of this grand unification, that you imagine that the gauge group is just SU2, which is the smallest non-abelian group. And you can work out the particle spectrum of this theory if you give it a Higgs field in the adjoint representation. You find by second quantization that means you turn, there are particles corresponding to the fields out of which you build the model. There are two heavy spin 1 particles. These are the two of the 3 gauge particles. SU2 has 3 gauge particles. And they have electric charge plus or minus Q. There's a massless spin 1 particle, which you can think of as the photon, and there's a spin 0 particle, which is the relic of the Higgs field, and in this case it's a massless one. The Higgs particle that people are looking for with these particle accelerators, of course, are heavy ones. But this is because we're considering a sort of, we're not quite considering the standard version of the standard model. I mean, we're considering one with a special sort of Higgs mechanism and a vanishing self-interaction of the Higgs field, because all the mathematical properties work nicely. It still has soliton. It has soliton solutions, and these turn out to carry magnetic charge. This is what 't Hooft and Polyakov pointed out. And there are 2 possible charges like that. So the spectrum of magnetically charged particles is very similar to the spectrum of electrically charged particles. That's the bizarre thing. And this led Klaus Monton and myself to suggest that actually there was a hidden symmetry in this theory. You could replace the electric charge by the magnetic charge, which was related by this Dirac quantization condition, and you could interchange the magnetic charge particle with the heavy gauge particle, and you got back a similar sort of looking theory. And this was supported by lots of the internal structure of this theory. You could do all sorts of calculations based on the precise equations, which I haven't written down. and see how this checked out. Other people were intrigued by this, and I didn't mention it, but there was an important paper by De Vecchia and Dada, and then there was a paper by Ed Witten and myself, and then there was a paper by Hugh Osborne, which pointed out in various stages that this special situation, I said there was a special situation here, it was almost supersymmetric. I haven't told you what supersymmetry is, but supersymmetry is a new sort of idea which sort of arrived with string theory, that there was a symmetry between fermions and bosons, integral spin particles and half-integral spin particles. And this particular model that Monton and I had considered, in the limit we had considered it, was sort of supersymmetric. It didn't have spin half particles, but you could add them without altering anything, so it became supersymmetric. And that's not true of a generic theory without fermions. You can't just add them and get a supersymmetric theory. It has to have some special features. Much later on, not much later on, there was the work of Manton, and then much later on was the work of Atiyah, Hitchin, and Ashok Sen, which culminated in 1984. They realized that you could actually construct solutions to this theory with lots of monopoles, and they didn't exert any forces on each other, so these solutions were stable. Then eventually Sen realized that this gave you a space of solutions with some arbitrary magnetic charge. There were actually states, sort of bound states of monopoles, stable solutions which you could construct. And I can't go into the details of it, but eventually it was realized that there was really a consistent picture which was much more complicated than had been originally suspected, in which everything worked much better than you had any right to expect. And one of the interesting features was, of course, because I said you replace Q by G, which is inversely related by Q, you relate strong coupling to weak coupling. So this is S-duality or electromagnetic duality. This was what grew out of these ideas. Now I don't have time to explain it, but this is something which sort of happens with something like a unified version of the standard model. Of course, beyond that, there's much more. People, including myself, have worked on superstring theory, which the reason for that is that it's something which sort of incorporates supersymmetric gauge theories, the kind that has electromagnetic duality, and incorporates it with gravitational theory, Einstein's general relativity, and so on. And all these phenomena generalize, and there's all sorts of complicated versions of it. So the idea keeps on going and developing. So this is what I've said here. And this is why I say the monopole is eternal, because the story of development of these ideas has not finished. There's undoubtedly a lot more to learn, but it is something really intriguing. And I hope I've convinced you of that. So I'll stop there. Thank you.
What is the expected mass of this particle?
Yes. No, there is a concrete formula comes out of these simplified models. The generic feature of this formula is that it is rather heavy. because of this inverse relation between the electric and magnetic charge. It's actually given by the same formula as the mass, because it's sort of symmetrically related to the gauge particle. The mass of the gauge particle is given by the Higgs mechanism in terms of the electric charge. It's some vacuum, some parameter times the electric charge. The formula for the monopole is the magnetic charge times the Higgs field. And because of this inverse relation, it's between the electric and the magnetic charge, it's obviously very large if the electric charge is small. But of course, that's what happens in this simple theory. If you have a more complicated theory, what happens will depend upon some complications in that more complicated theory. So this is sort of good news in that you know, it makes it more difficult to see this magnetic monopole because it's much heavier, but it does mean that sooner or later we either have to see it or admit that this is wrong or that there's something very different, and I suspect that is the conclusion, that there is some extra twist in this story. That's why I mentioned these stories of the non-abelian gauge particles. There have been several twists in that story. It appeared all wrong at first, and then there were unexpected new developments like asymptotic freedom and the Higgs mechanism, and then suddenly, click, it all fitted with the physics.
Any other questions? No. Very clear, very nice.
Okay.
This sections idea, this is what Wu and Yang was
Yes. This is the Wu and Yang argument. Yeah, I didn't say that. Yeah.
But actually, that's the clearest way to derive.
Yes. No, I think so. That's why I did it. It's clearer than Dirac's way. Yeah.
That's zero inside. Oh no, this is the other scheme.
No, there isn't a Z0 in this simple model, the SU2 model. There's only the photon. Of course. Yes, I know. So it's not a physical model. That's right. Yes.